Hello, my name is Logan Horowitz. I'm a second-year PhD student in the Palawa group at UC Berkeley. I completed my undergraduate degree in electrical and computer engineering in 2019 at Cornell University. Today I'll be talking about optimization of power converters through advanced design methodologies. More specifically, I will focus on a software package I have developed which can efficiently compute the parasitic inductance of a printed circuit board design. These inductances greatly hinder performance in power conversion, and it will be essential to overcome this challenge in order to progress the field. For some background, we can look at the top left of the poster. Power supplies are ubiquitous in everyday life, showing up in electric aircraft, electric cars, renewable technologies, wireless charging, etc. These supplies rely on switching between different circuit states depending on how much power is needed in the application. These switching transitions are ideally instantaneous and lossless. In reality, unwanted effects arising from the design of the supply will cause harmful results such as voltage ringing, electromagnetic interference, and poor efficiency. To predict these effects, the value of parasitic inductances must be determined. I have developed an analytical approach which takes the physical design of the converter and converts it to a straight perpendicular segments as shown in the bottom left quadrant. It then divides these down further into a fine mesh and uses Maxwell's magnetism equations to extract an overall parasitic inductance simply from the geometry of the design. In order to validate this approach, I have compared the results of the proposed program to other tools for estimating inductance which are typically used. The first is a highly detailed finite element solver software, which is much more complex and also requires the use of a proprietary software. The next is a time domain measurement where we attempt to switch the converter and look at the voltage ringing that occurs in the circuit. The final test is done by using a piece of equipment called an impedance analyzer to directly measure the inductance. The bottom right quadrant shows a printed circuit board which I designed for these tests. It contains various unit converter cells and some calibration structures. The results obtained using the proposed approach show very good agreement between those found using the other methodologies. This program will allow us to quickly predict parasitic inductance before fabrication and optimize the design accordingly. This work is ongoing, and we are looking to automate the converter design process based on this software and even make recommendations for component selection and the physical layout of the power supply. Eventually, we hope to make it open source such that all power supply designers can take advantage of the platform. We believe this will help to propel us toward the future of fully optimized power converter design, enabling advanced technologies such as commercial electric aircraft. Thank you for your time.